You know, all around us, our entire modern world is running on a hidden set of rules. It's like an invisible blueprint that keeps us safe every single day, especially from something as powerful as the electricity that's flowing all around us right now. Today, we're going to pull back the curtain on that blueprint, and it all starts with a little bit of a mystery.
So, to get us started, I've got a question for you. What on earth could these three very different numbers possibly have in common? Let's take a look. First up, we've got 1.25 meters. It's a really specific measurement, right? What could that possibly be for? Just try to hold that number in your head for a second.
Okay, next, a nice round 1 meter. Simple, clean. How does that connect to the last number?
And finally, 5 ohms, which is, a unit of electrical resistance. So, what is the connection? Well, these aren't just random numbers I pulled out of a hat. They are absolutely critical parts of the electrical safety code, this super detailed rulebook that protects you and your home and your office from electrical danger every single day. Let's break it down. We're going to start in the most familiar place possible, probably the room you're sitting in right now, because the code is incredibly specific about the stuff you interact with all the time. Remember our first number. Boom, here it is. 1.25 meters. That is the standard required height for a light switch. Now, this isn't just some random design choice. It's a rule that's all about consistency and making things easy to use. It means that no matter what building you walk into, you instinctively know exactly where to reach to turn on the lights. Now, when it comes to sockets, the rules get even more specific, and it's all about context. So in a kitchen, they've got to be 23 centimeters above the counter, to avoid spills. In an office, that same height above the floor is fine. But in bathrooms, nope, absolutely no sockets allowed. It's a huge no-no. Water and electricity just don't mix, so any switches have to be way up high and a good meter away from the shower. Oh, and to stop you from overloading the system, any single power circuit in your house can't have more than 2 sockets on it.
All right, now let's go behind the drywall. Let's see how all this stuff connects. We're going to explore the hidden infrastructure. Think of them as the secret highways that carry all that electricity safely through the building.
See, wires don't just hang loose inside your walls. They're actually protected by this armor called conduit. In really heavy-duty places, like factories, you'll find these thick, threaded steel conduits. But in your house, it's probably a non-metallic PVC. It's lighter, yeah, but that doesn't mean it's less regulated. It has to be securely fastened to the wall with these little saddles every 60 centimeters, just to make sure it's not going anywhere.
And the wires inside that armor, they're different too. A circuit for your lights, which doesn't draw a lot of power, can get away with a thinner 1.5 square millimeter copper wire. But a power circuit, the one for your outlets that might be running a computer or a microwave, that needs a much thicker, beefier 4 square millimeter wire. And that difference is absolutely crucial. Using the right thickness prevents overheating, which is a huge deal for fire safety.
The level of detail in this code is it's incredible. It turns out, even bending a high-voltage cable has its own set of very strict rules. You can't just fold it around a corner. The tightest you can bend it is based on a multiple of D, and D is just the cable's own diameter. Why? Because if you bend it too tightly, you could actually damage the wiring inside, creating a massive failure just waiting to happen. This table makes sure every single turn is a safe one.
Okay, let's move to the brain of the operation, the central hub where all these protected wires come together. We're talking about the distribution board. You've definitely seen one of these in your home or office. It's that metal box with all the little circuit breaker switches. The distribution board, or DB for short, is the command center. It takes all the main power coming into the building and safely splits it up, sending it off to all the different circuits for your lights, your outlets, and your appliances. And hey, there's our second number from the intro, 1 meter. According to the code, you have to have at least 1 meter of clear, totally unobstructed space right in front of any distribution board. Why? Well, think about it. In an emergency, if you need to shut off the power fast, the last thing you want is a bunch of boxes or furniture in your way. It's a really simple rule that could literally save a life. So we've talked about protecting wires and making sure we can get to the controls. But now, let's get to what might just be the single most important and maybe the least understood safety feature in the whole system: earthing. The best way to think of earthing, or grounding, you might have heard it called that, is as an emergency exit for electricity. If something goes wrong, like a live wire accidentally touches the metal case of your washing machine, well, that dangerous electricity needs a safe place to go.
The earth wire gives it a path of least resistance, channeling all that current safely into the ground instead of, through you. And creating this escape path is a serious piece of engineering. You can't just stick a wire in the dirt and call it a day. A proper earthing pit has to be a specific distance from the building, with these electrodes buried deep in the ground. We're talking 3 meters deep sometimes. The whole thing gets tested, and then it's sealed up with a heavy, locked cover. This is a meticulously planned process, not a suggestion. And this brings us to our final mystery number, 5 ohms. For that emergency exit to actually work, the path to the ground has to have really, really low resistance. So the code says that resistance must be less than 5 ohms. That low number is what guarantees that if there's a problem, the electricity will take the safe path to the earth instead of any other path. This little number is the key that makes the whole safety system work. So, we've gone from your light switch, behind your walls, to the control panel, and all the way down into the ground. Now, let's zoom out one last time and see how your building system connects to the much, much bigger electrical grid. The rules do not stop at your property line. Here's a number we haven't seen yet, 3.7 meters. That is the minimum vertical distance that high voltage lines, up to 33,000 volts, have to stay away from the very highest point of any building they pass over. It's a massive safety buffer zone designed to prevent any kind of accidental contact. And the infrastructure that's needed to take that super high voltage power and bring it down to a level we can actually use in our homes, it's huge. This table just gives you a little taste of the physical space it takes up. A substation for a big apartment complex could take up over 180 square meters. That's the size of a small house, just filled with equipment to keep our power safe and stable. So here's the real takeaway. From the height of one little socket in your kitchen, all the way up to the clearance for a massive power line, every single detail is part of this huge interconnected system. This invisible blueprint, it's really a masterpiece of engineering, and it's designed with just one primary goal: keeping us all safe.
It really makes you think, doesn't it? What other invisible rule books are out there, quietly managing our world and keeping things running? From the water in our taps to the data on our phones, what other complex systems are working perfectly for us right now, just out of sight? Something to think about. Thanks for joining me.